So, hey friends, welcome back to Wired Intelligence, our neural series. In episode 1, we built a simple neural network from scratch with one hidden layer and it learned the XOR logic gate. We understood how the network thinks, learns, and improves. That was a big baby step for us. But here is something exciting. Today we go deeper, literally. Today's episode is called The Power of Layers. And that's because modern AI, from ChatGPT to self driving cars, uses layers and lots of them. But what does a layer actually do? And why does adding more make the machine smarter? Today we will answer that by building a deeper neural network with two hidden layers. Then will explain our code and show the machine learn the XOR even better. So now comes the part like what is layer or what is layer are really. Before we code, we need to see something, like we want to know about what is layer and why one should know about this. Like, think of a neural network like a factory. The input layer is like a raw material entering. Like in the previous video we watched, we knew that we have our input layer, we have our hidden layer, and finally we had our output layer. There we saw we had two inputs. We had one hidden layer with four nodes and our one output node. Now what does it do? The input layer is like raw material entering. Here let's say we're entering as a raw material, and the each hidden layer transforms it a little bit, and the output layer gives you the final product. Each neuron in a layer is like a tiny worker doing a calculation. It takes input, applies some weight and bias, and gives an output using an activation function. We will use sigmoid again. So what we can say is, let me just remove. What we can say is, if we have more layers, it is like the more transformation, and it is likely the machine will be able to handle more complexity. So, just like a multi-stage production line, it can make a better product. Now, we will visualize our XOR again. We have seen our XOR logic. The XOR, what was that called? The XOR, like the truth table one. Yeah, I forgot that for a moment. Yeah. If we draw the XOR truth table here, let's say I have 0 0 0 1 1 0 1 1. Now if we do the XOR truth table, we completed that earlier, so we knew that if we have a common value like both are 0 or both are 1, it returns as a 0, and if they are different, they returns as 1. So this was our input, this is another one, and this is A XOR B. Now if we visualize our XOR more to understand like why we even need layers, this is simply our truth table. Now if we want to plot this thing, like let's say if I want to plot this, don't mind if the line goes curved a bit. So yeah, let's say this is our 0, here we have our 0, here let's say we have our 1, and this is our 1. Let's say let's imagine in this axis we have our one of our input A, and in this axis we have our let's say for this one we have our A, and for this one we have our B. Now if we plot this at 0 0 point, we have our 0. If we have our A at 0 and B at 1, we have our output here. If we have our A input as 1 and B input as 0, it gives us here, and if both are 1, it returns us here. Now if you look more properly, like this one is for our 0 0, this is for our 0 1, this is our 1 0, and this is our 1 1. So what I am trying to say is, here a straight line cannot separate these things linearly. Like if we look, what we can say, what I'm going to say is like this is more like let's imagine like if you were something familiar with a circuit, like if we have let's say I have a 5 volt here and I have a 0 volt here. Like if I have a signal here, if I have 0, I have no volts, it gives us 0. Or if I have a voltage, like here at first 0, then 5, then again 0, then again 5, if it goes this way, here it will be 1, or the positive, it is have some power, and here it is negative, or you can say 0. So here our this one is positive, this one is positive, and these two are negative. So from here you can see like we can't separate these two things like linearly. A single neuron can't literally solve this. Even one hidden layer sometimes struggles to perfectly fit XOR with certain weights. That's why we will use two hidden layers in this episode. Now this was our basic of like why we will be using more neurons. So now let's see, we know about our the activation function. Okay, so every neuron ends with an activation function. As we know, it decides like should I fire or not. We will use the sigmoid function again. What it does, if you remember from the previous video, It squashes the values between 0 and 1. It's smooth, predictable, and easy to understand. If you have some idea about the sigmoid function, like for the activation function, here we are using the sigmoid. Like if I draw the curve here, let's say here, here it is 0, here it is 1, here let's say it is 0.5. It is the curve goes something like it can go wrong, like it intercepts here, and yeah, it is something like this. So here you can see it squashes our values between 0 and 1. Now what we do is, when we pass the values through sigmoid, the output becomes something like 0.7 or 0.1, a soft yes or no. We will use it for all layers today. Now comes the fun part. Now we will code our this project, and for a quick reminder, you can find the GitHub repository in the description below. Here you will find the upcoming video titles or upcoming collab links, the notebook links. Also you can find the YouTube video links there too. You can fork it, you can if you want some issues, if you find some issues, you can raise some issues, and I will try to sort that out. Now let's move on to our code. Now what we are going to do is, before jumping into like the code, I forgot something, like just yeah. So like first, let's say, like, what are we going to build today? Like we are going to build something like we in the previous videos we have like, for the, let's say, if we don't just draw, if we write, like if we had the inputs, we had hidden layer, and then we had our output, right? We had two inputs. We had our one hidden layer with 4 neurons, and we had our one output or 1 neuron. So what are we going to do today is, we will be having some crazy things, like we have same as like there will be 2 input neurons, but there will be 2 hidden layers. What we are going to call that, we will be calling that hidden layer 1 and our hidden layer 2. Now, and then again we will have our output. So here what are we going to have is, we will be having our 5 neurons at our hidden layer 1, and we will be having 3 neurons at our hidden layer 2, and as usual our output 1. Now if we want to like draw this thing, like here you can see, here is the 3 layers of learning, like from here to here, then from here to here, and finally from here to here. Now if we want to draw this, what are we need to do is, like let's say I have an input, then let's say HL1 as hidden layer 1, HL2 as hidden layer 2, and output. So we will be having 2 inputs. At HL1 we will be having our 3, 4, and 5 neurons. Then here we will be having our 3 neurons, and finally 1. Now like it will look something like this. Let me draw it first. This, from this to this, and this to this, and again this to this to this. So the neurons or our neural network will look something like this. Here you can see like it will learn in these three steps here, like this one here, this one here, this one here, this one here, and finally this one here. And finally it will conclude, or it will give the output here. So this will be our neural network, like this is how it will learn today. So now let's code everything from scratch using just Python and NumPy, like a true AI engineer. Now let's go to our Google Colab. As we said, we're going to use just Python and NumPy. Now we code. At first we will be importing our NumPy as np, and then what are we going to do is we're going to use the sigmoid function. We saw that like how we do this, the sigmoid of x, and then we do the return 1 over 1 of 1 of 1 divided 1 of np dot exp of minus x. Yeah, that was our sigmoid function. Now we write the sigmoid derivative. Let me write in the same block here, sigmoid derivative here for x. Now we return the x multiplied 1 minus x. Yeah, this helps us calculate like how much to adjust the weights during the learning. Now we use like we give our input neurons like from x, let's say the np array. We won't use like this. We will be having just 0 0 0 1 1 0 and 1 1. Yeah, this is it. np dot array. Yeah, this looks good. Now if we move, and as you know, this is our XOR data set, or the like what are we going to use in. So like now let's say what we do is np dot, we do the random dot seed. We will be giving seed times of 42. What does this do is it ensures we get the same random weights every time, makes our testing more easier. Now let's do the weight of 1. It will be like np dot random not here it will do the random, and this will be doing our 2 and 5, and 1 of 5 we will be, yeah, here the now for weight 2, right? This for weight 2 it will be something like the 5 to 3. like we seen like here from 2 to 5 and 5 to 3. Yeah, like this will be 5 to 3. Yeah, now if we write the bias here, the bias will be our np dot zeros. We will be having at first our 1 to 5 and then 1 to 3, our 1 to 5, and for bias 2 we will be having np dot 0 1 to 3. Yeah, this looks great. And again we will be having our another weight. I totally forgot that our weight 3 here, np dot random, it will be 3 to 1 from like as you can see from 3 to 1. So if I want to like break down this, like for weight 1, weight 1 works here from 2 to 5, and then our weight 2 5 to 3, and for our weight 3 3 to 1. So if we do the b3 here, np dot zeros, the zeros bruh, yeah, if we do the zeros here, we will be having our 1 to 1. Yeah, I think this looks great. Now let's move on. And for like your information, like bias starts at 0 and then it randomly like changes and like train your model. Now we train our model like for 10,000 times, so I will be using for epoch in range of, let's say, 10,000. And now we write down our inputs like for the forward pass code. Here we will be having our z1. Here for z1 we will be using np dot yeah, first let me like check x and w1 plus b1 and a1 of sigmoid of z1 z2 np dot of, yeah, weight 2 and bias 2 and sigmoid of z2. Yeah, now also we need to do for the output neuron like the z3 here, np dot, we do our, yeah, a2 and w3 plus b3 and sigmoid of z3. Now what does this do? Like for this one, it is doing the input goes through our first hidden layer like the dot product, then we apply the bias, and then we use the activation. Like if we show, it is more like if I remove all this, like it is more like from dot product, then it uses the bias, it applies the bias, and then it uses the activation function. So this is how it goes. Now if we move on, like here in this part, it is like output of, it gets the output from the first hidden, becomes the input to our second hidden, and finally here our final prediction from the output neuron. Now what we are going to do is we will be doing the backward pass. Now here at first, let's say the error here, like it will be a3 minus y, our y is this array, and then we will be doing the dw3d respect, yeah, the np dot the a2 of t error. We do this like later, and error, and for the db3 we do the np sum of error multiplied by not this one. We will don't use this error. The axis will be 0 and the keep dimensions true. Yeah, now the network sees its error and like it adjusts weight at the output. Now we do for the error 2 here. Error 2, what we do is we do the np dot, like let's say do this and check this, like np dot error of w3 t and sigmoid derivative of a2. Yeah, now dw2 np dot a1t of error 2, and yeah, what does this block do is it like error flows the backward to our second hidden layer. Now for our like error 1, what are we going to do is np dot, let's check, like this is helping us a lot. Like we don't need to write a large some number of codes. Like we just check like how this it really works or not. Like here for error 2 and with respect to t sigmoid, yeah, this looks good. xt and error 1, yeah, this looks good. Now what are we going to do is we will be uh, updating the weights. Let's see, what are we going to do is we are going to, let's say if we update our weights here, like rw3, yeah, let me give some space here. Now what we do, we update all the weights and biases using a learning rate of 0.1. Our w3 will be minus equal of 0.1, 0.1, and it will be multiplied with our derivative with respect. Yeah, now for our b3 we do the same, 0.1 multiplied with our derivative 3. Now for the dw, just let me like just copy this thing and just this will be, yeah. Now let's just change the values here to 2, and this will be 1 and 1. Yeah, let me now just change it here to 1 and 1. So now the final part, like, and for every 1,000 step we print, we check the progress. For that we, let's say we run an if else statement here. If epoch like 1,000 yeah equals 0, it loss, we should print the loss or not. We don't like print, like let's see, we print the f string of epoch of our, like the epoch here, like let's just check like if this works. We're hoping for the best. Now we print our final, we print our like our final prediction here, and here we will be like printing till the we will be printing our A3 of like for we round it up to like so it shows our like perfect result. So yeah, I hope this works. Yeah. What is this showing? Tuple object cannot be interpreted as an integer. What? np random dots. Yeah, like my bad, it is denoting this as a tuple. Didn't saw that coming. Yeah, now it should works fine. Let's see. Yeah, here epoch 1000 2000. Yeah, here you can see our final prediction 0 1 1 and 0. As per our like our truth table, we saw for 0 0 it will be 0 1 0 1, and for 0 1 it will be 1, and finally 1 1 it will be 0. So this is how you can like you can see like the machine has successfully learned the XOR logic with the help of layers. Like you can think of each layer as a stepping stone, each one transforming the data just a little until it gets the right answer. So like it was so much fun doing this. So what we learned till now, let's recap a bit. We used only Python and NumPy to solve this whole thing. We built a deep neural network with 2 hidden layers. We taught it to solve a XOR. We like learned how forward and backward passes work, and we watched the model learn line by line. This is the beginning of what deep learning is. You just made your own mini brain. That's for today. In episode 3, we will go visual. We will plot how training accuracy improves over time. We will show you how to graph the loss. And finally, we will begin looking how this could be used for things like image recognition later. If you found this useful, please give the video a like and comment layers unlocked so I know you made it to the end. Subscribe to catch the rest of word intelligence. Thanks for learning with me. Until next time, goodbye.